This is 13.3. So this video will be just 13.3. Super important topic, dot product. So we said in the previous lecture that there's a couple operations we could do with vectors. We can add them. We can scalar multiply a number to a vector. But we said there wasn't a good way to multiply two vectors. Well, the dot product is one way to kind of multiply two vectors together. But in a way, it's different from what you might expect. So let's start with notation. U, if we have a vector u, if we have a vector v, we can take the dot product. Notation is like this. Use a dot right there. And the words would be u dot v. Right? So you never say u times v. You never say u multiplied with v. You say u dot v. All right? Because the next section, 13.4, will be a different kind of product called the cross product. It's going to look like this. And that's going to be an x kind of. And so you never ever want to confuse the two because they're very, very different operations. Okay, so the dot product is, the notation is u dot v. Oh, by the way, this could be a vector in the plane, could be a vector in space, anytime, any kind of vector. All right, so I'm not gonna, I don't have to specify whether we're in the plane or in space yet. Okay, so the important feature, first of all, is that this guy here is a scalar. All right, so it's not a vector in particular. Okay, so that's what I mean by this kind of multiplication is somewhat weird or maybe unsatisfactory in a way, because normally, right, if you have 3 times 5, 3 is a number, 5 is a number, but 3 times 5, is also a number. Here you have u as a vector, v is a vector, but u dot v is not a vector, it's a scalar. Okay. Nevertheless, this scalar is very important, this u dot v, the result of u dot v, and gives us a lot of information about u and about v. Okay, so the deal is here. The book introduces the dot product by doing, in a way, by taking the graphical point of view, but I'm gonna do it differently because I don't like the way the book does it. Because the book writes down a formula for the dot product, and it's a completely mysterious formula that seemingly comes out of nowhere. So I'm going to introduce the dot product in a different way. I'm going to introduce it in the kind of algebraic way, like this. So if I have u, so I'm kind of just going to do it by example. So let's say I have a vector u, and it's 1, 3, 5. Let's say I have a vector v is 2, minus 1, 7, right? What's u dot v? So the good news is super, super simple. So the definition of the dot product, at least from the algebraic point of view, is super simple. You take each entry of u, multiply it with the corresponding entry of v, and then you add up all the results. So 1 times 2 plus 3 times minus 1 plus 5 times 7. All right, what is that? That's going to be 2 minus 3 plus 35, so 34. Okay, that's it. That's the dot product. That's how you compute the dot product. This example was for two vectors in space. If you want to talk about vectors in a plane, just erase this guy, and erase this guy. And you would get -1. All right. So same idea. If you have a vector with 4 entries, multiply the first entries, add it to the product of the second entries, add it to the product of the third entries, add it to the product of the fourth entries. All right. So super easy to compute. That's actually really, really important, and it'll help us do a lot of things. Okay, Now, why would we want to care about such things? Why do we care about this kind of algorithm for kind of interacting two vectors with each other? Well, what you can do is you can take this vector u, you can take this vector v, you can put them together like this, and you can consider the angle between them, and you can close this guy off into a triangle. And if you analyze the trigonometry that goes on here, specifically using the law of cosines, so remember all the way back whenever you took trig, there was the law of cosines that you probably thought was completely useless. Well, using the law of cosines, what you can actually compute, doing, again, just kind of thinking about the trigonometry of a triangle, is that u dot v turns out to be equal to length of u, length of v times cosine of the angle between them. All right. Now, I'm not going to actually do it for you. You can if you want. Just write down the law of cosines all the way back from trig, and you know, kind of work through it, and you might be able to get it. You should be able to get it. All right. Okay, just as a fun exercise. By the way, this kind of makes sense because right, the law of cosines involves an angle, right, and then the two sides, and then the opposite side. Okay, so we see the angle here. We see the length of a side. We see the length of another side. Okay, all right. So we're not going to explain this. This is something that you definitely need to know, though. First of all, like I said, you need to know how to compute in this super easy method, but you also need to know this kind of geometric or graphical interpretation of the dot product. Okay, so again, in short, the dot product tells you basically about this angle right there. All right, let's kind of see why this is true. For example, let's say I calculated the dot product of these two vectors, and I discovered that it was bigger than 0, right? What does this tell me about the two vector, the kind of relationship between u and v? Well, how could this be positive? U dot v is equal to length of u, length of v, cosine theta, right? Well, length of u is going to be positive, right? Length of v is going to be positive, again, as long as u and v are not the 0 vectors, right? And so what that means is cosine theta has to be positive, right? If this guy were to be true, u dot v were to be positive, then cosine theta has to be positive. Okay. When is cosine theta positive? Well, here's the graph of cosine, and it's positive from 0 to pi over 2. Right? So the angle, our conclusion here is that if u dot v is positive, then the angle between them is between 0 and pi over 2. All right. Okay, so maybe something like in this picture above. Oh, by the way, I should probably mention, when we say the angle between two vectors, actually, technically, there's two angles, right? Whenever I draw two vectors like this together, there's actually two angles formed by the vectors. There's this angle right here, and then there's the angle that goes all the way around the other direction, like that. All right. When we say the angle between two vectors, we always mean the smaller of these two. All right. So in this case, it would be this guy right here, as opposed to the big long one on the outside. All right. So always the one that's less than or equal to 180 degrees or pi radians. Okay. In any case, so that means that when I draw this picture, the only relevant parts are the ones to the left of this dotted line, right? Because our angle is always going to be between 0 and pi. Okay, so if u dot v is bigger than 0, then the angle between the two vectors is not too big. All right. Seems perhaps not too useful, but it can be useful, right? So if I gave you 3, 1, 2, and 4, 1, -1, right? And I ask you, what's the angle between these two vectors? Is it big? Is it small? How would you actually do that? How would you calculate it? Well, maybe you'd have to draw the two pictures. You'd have to do some trigonometry. Huge pain, right? But now I can just take the dot product between the two. The dot product is going to be here 12 plus 1 minus 1. So the dot product is 12. 12 is bigger than 0. And so I know the angle between these two vectors, whatever they happen to look like. I don't even have to draw a picture. I know the angle is less than 90 degrees. Okay, what happens if u dot v were less than 0? Well, again, u dot v is length of u, length of v, cosine of theta. This guy here, length of u is positive, length of v is positive, it certainly can't be 0, or else we can't get this less than sign here. So that means the cosine is negative, right? Okay, for the cosine to be negative, again, we look at the graph of cosine between 0 and pi. It's got to be here, right? So that means that the angle between u and v has to be bigger than pi over 2, and of course less than 180, so less than pi. So perhaps u and v might look something like this, right? With this angle right there. Okay. So again, we get information about the relationship between u and v just from the dot product, which again, super easy to compute. All right, that's actually really important. Okay, the last one is the most important one of the three situations, is if u dot v were equal to 0, right? How could this happen? Again, u dot v is length of u, length of v, cos theta. Okay, for something to be equal to 0, for a bunch of products to be equal to 0, one of these guys has to be 0, right? If two things are multiplied, x times y equals 0, that means x equals 0 or y equals 0, right? So in this situation, either u is 0, the 0 vector, or v is the 0 vector, right? Those two cases are kind of uninteresting because obviously the 0 vector dot another vector should be 0, right? Just from the way we define the dot product. Or cosine of theta is 0, right? Well, this is the interesting one. If this guy were 0, what situation are we in? Again, let's draw the graph. That guy right there. So cosine theta is 0 when theta is pi over 2. Okay, so what that means is u and v are perpendicular. Okay, again, this is assuming u and v are not, neither of them are the 0 vector. Okay, this is the most important, probably the single most important application of the dot product. It allows us to tell when two vectors are perpendicular. Okay, and again, if I just gave you the coordinates, of two vectors, 3, 1, 4, and 5, 2, -10, right? And I asked you, are they perpendicular? If you didn't know anything about the dot product, you maybe have to sit down and do a whole bunch of trig or a lot of work. Now, all you have to do is take the dot product of the two, check if they're equal to 0, right? If they are 0, then it's perpendicular. Okay, so an enormous amount of information about the relationship of the two vectors you can get just from a simple addition and multiplication computation. Okay, by the way, another word for perpendicular that we frequently use in math is orthogonal. All right, I'm going to use these two words interchangeably. And notation-wise, perhaps we might use something like this. U is perpendicular to V. Okay. Vectors being perpendicular, super important. All right. Whenever you have perpendicular vectors that you're working with, you're very happy because it means in a way that the two vectors interact in a simple way. Well, literally in a simple way, right? Their dot product is equal to 0. Okay. Let's see. So next, let me write down some properties of the dot product. Actually, let me, let me do one more thing related to our discussion just now. Let's be actually a little bit more precise than we have been just now, right? So just now, we talked about u dot v positive. We talked about u dot v negative. We talked about u dot v equals 0. But let's be even more precise. So let me write down u dot v equals length of u, length of v, cosine theta. All right. Now, let's look at which things are easy to compute. This guy, easy to compute, right? All you need to know is actually just addition and multiplication. This guy here, easy to compute, right? How do you compute the length of u? All you need to know is how to square things, to add, and then to take a square root, right? This guy here, just as easy. Okay. This guy here, cosine theta, hard. Again, you have to do some trig in order to figure out the angle between two vectors, right? So ultimately, what we can do is we can take this point of view here. Cosine theta is equal to u dot v over length of u, length of v. All right. So everything on this right-hand side is easy, right? So what happens is this is kind of an extension of what we just talked about. Because everything on the right-hand side is easy, then the moral is that the dot product tells us about angles, right? And in fact, it tells us literally the angle between u and v is this guy right here. So you literally have a concrete formula for the angle between two vectors, right? A concrete formula for this guy right there if you need it. All right. We're not going to use it too much in this particular formula in our class. Again, like I said, the most important kind of feature is actually the dot product equaling 0, meaning things are orthogonal. But the dot product does tell you about, can compute for you literally the angle if you need it. Okay. If you look at the extra credit problem on this week's paper homework, which I highly recommend you do after this lecture, as opposed to maybe at the end of the a week before you turn it in. If you look at that extra credit problem, it discusses the idea of the dot product for things that perhaps are not as well, for things that aren't vectors that maybe you don't expect have the concept of a dot product. All right, pretty interesting. So take a look maybe after this lecture. Okay, let's see. Oh, so let me do one more thing before we actually talk about properties. So notice another thing. So u is equal to, let me just do this again with a numerical example, 1, 3, 5, right? What is u dot u? That's going to be 135 dot 135, right? Always put the dot, by the way. Always put the dot. Don't just write u, sorry. I always put the dot so it comes naturally. Don't put u like this. That has no mathematical meaning. All right, so be very kind of disciplined again and always put the dot. Okay, so 135.135, what is that? That's going to be 1 times 1, which is 1, plus 3 times 3, which is 3 squared, plus 5 times 5, which is 5 squared. And what is that? That's the same as the length of u squared, right? Remember, the length of u is the square root of this thing. So this is equal to actually length of u squared. Okay, so this is actually an important feature of the dot product, that a vector dotted itself is just the length of the vector squared. Okay, and again, if you look at the extra credit problem, what happens is, I guess I should just say it. You're going to define, or hopefully you're going to try to define, the dot product between two functions. And once you've defined the dot product between two functions, then you can define the length of a function using this expression right here, right? If I have a definition for the left-hand side, then automatically, in a way, I have a definition for the right-hand side. Okay, so I can define the length of a vector as the square root of the dot product. The length of a function as the square root of the dot product of the two of it with itself. Okay, super interesting. That leads to some really, really interesting math and really, really interesting applications. Okay, so again, take a look at that maybe after this lecture, and if it's too mysterious, come to the Zoom meeting on Thursday and we can talk about it. All right, let's talk about some properties. So again, like I said in the last lecture, whenever you kind of add a operation to your kind of mathematical object, you like to know what properties those operations have, and you would like to know how this new operation interacts with whatever other operations you have. Okay, so let me write down the interaction of the dot product with the vector addition. Okay, so u dot v plus w. If you write this all out using our definition of dot product, you'll see pretty easily that this is the same as u dot v plus u dot w. Okay. So basically, you think of it as dotting here and then dotting there. Okay. All right. This is why we call the dot product a product. It's because it satisfies the distributive law, right? Which is what products should always satisfy in relation to the addition operation. All right. Okay, so that's how the dot product interacts with addition. How does the dot product interact with scalar multiplication? Well, C u dot v. This is equal to cu dot v, and that's equal to u dot cv. Okay. So again, notice this looks each side looks kind of the same, but actually interesting things are happening. Here you're doing the dot product of two vectors first, and then multiplying the number c to the result. So this multiplication right there, c times this is multiplication of numbers. So let me call it regular multiplication, right? Because again, u dot v is a number, c is a number, so c times a number is a number. Okay. However, on the right-hand side, this product right there is a dot product, right? Because c times u, scalar multiplication, gives you a vector. V is a vector, so c times u dot v, right, is the dot product. As opposed to, again, on this left-hand side, that multiplication is actually regular multiplication. Okay, and on this right-hand side, the regular multiplication, you actually don't see a regular multiplication. You see scalar multiplication of a number with a vector, right? You see the dot product, but there's no regular multiplication. Okay, so this is kind of this is how the dot product interacts with the scalar multiplication. Okay, let's see other properties. So these are kind of native properties to the dot product. Those were kind of interactional properties between the operations we talked about before. This next one is one that is native just to dot products. U dot v is the same as v dot u. Okay. Again, why is this true? Just write down the definition of the dot product, right? Because regular multiplication, the order doesn't matter. This one is not going to matter as well, right? So let me do an example with I guess I haven't done an example with vectors in a plane yet. So 1, 2 dot 3, minus 1, right? That's going to be 3 minus 2, right, which is 1. And of course, if I do it the opposite direction, 3, 1 dot 1, 2, I'm going to get the same thing because 3 times 1, 3 minus 1 plus minus 1 times 2, this gives you the 3, and this gives you the minus 2. So you still get 1. Right? So ultimately, because regular multiplication, the order doesn't matter, right? It's commutative in kind of more mathematical terms. So is the dot product. Okay, another one that I just talked about actually. U dot U is always bigger than or equal to 0. And it's equal only when, that's terrible. Only when U is the 0 vector. Okay, so we saw that. The reasoning behind this is, let me put that in parentheses. The reasoning behind this is that U dot U is equal to, we just saw, it's the length squared, right? And so the length of a vector is always positive unless it's the 0 vector, in which case the length is 0. So that covers this stuff in the parentheses right there. Okay. Let's do an application, or kind of an application. Orthogonal projection. So mathematically, this concept is going to be super, super useful for our class. It's going to be super useful in your linear algebra class, perhaps next semester. It's super useful in all of mathematics. And it's super useful in real life because it actually is what gives rise to a lot of the compression techniques that are used in real life. So, compressing music, compressing a video file. A lot of that stuff depends on, pretty much all of it depends on orthogonal projection. All right. Okay. And we'll see an example, a kind of physics situation where we might want to need it at the end of this section. Okay, but for now, let's just concentrate on the math. So let's say I have two vectors, u and v. Okay, let me also draw the angle between them because we're talking about the dot product, and so the angle between two vectors is often going to pop up. Okay, so in a lot of situations, we're going to want to know, if we have two vectors like this, we're going to want to know, if I drop this perpendicular down here, we're going to want to know this vector right there. All right, so the question is, what is this vector? Okay. One situation where we might want this is perhaps v is a very important vector, and it has some special meaning. So you would like to write any other vector you come across, for example, u, in terms of v, right? Or you might want to understand how the vector u, right, how much of u lives in the same direction as v. That's essentially what this guy we're looking for. That's what it is. Okay, how much of u lives in the same direction as v? Okay, so this guy is so important that we actually have some special notation. This vector right here is called the projection of u onto v. All right, so you write a little v down here and the big U up here. Okay, so you're projecting u onto v. That's the guy we're looking for. All right. Okay, so how do we calculate this? Well, a vector is made up of a length and a direction. So if I can calculate the length of this guy and I can calculate its direction, then I'm all set. Okay. All right, first of all, it's direction. Let's do the easy one first. The direction is obviously just the same direction as v, right? Or maybe the opposite direction, depending on the relationship between u and v. But essentially the same, it's a vector that points, kind of along the same line as v. Okay, so I'm going to express this direction in terms of a unit vector. All right, so the direction of the projection is essentially this guy here, right? Or the opposite. Okay. All right, but in the picture that I have, that I've drawn right now, it's actually the same, exactly the same direction. Okay, let's calculate the length. Oops. So what's the length? Let me redraw the picture here. This guy here is theta. This vector is u. This vector is v. And what we have is we have a right triangle right there. And so we're going to use our knowledge of trig. If I look at this length, this is the hypotenuse of my right triangle. The length of this guy is length of the vector v. All right. So cosine of theta is equal to adjacent. This is the length that we were looking for, right? Right there. We want that length right there. It's going to be the thing we're looking for over the length of u. Okay, so instantaneously, I get that the thing we're looking for, the length of the projection, is u times cosine theta. Okay. All right, now, the problem is this isn't very useful to us because, if I give you the coordinates of a vector u and then give you the coordinates of a vector v, how would you actually go about finding the theta? It's a huge pain, right? Even if you kind of use what we talked about earlier with the dot product, up here, it's kind of a huge pain. You have to take an arc cosine and all that business. But we're actually in luck in this particular situation because what I can do is I can write this as length of u, length of v, cosine theta. So what did I do? I fabricated a v, and then I'm going to compensate for that by dividing by v. All right, so this is obviously the same as the line above because the two v's cancel. The two length of v's cancel, right? Why would I, do something, make my life look more complicated? Well, because the top here is actually just the dot product, u dot v. Okay. And again, I'm using this picture where the angle between u and v is acute. So this u dot v is actually positive. So the length we're looking for is actually going to be a positive number. All right. Okay, so in the situation where the angles are obtuse, like this, the argument is pretty much the same, except you have to worry about some minus signs, but they all work out actually perfectly. And maybe that's a good exercise for you to do, just to see if you understand this argument that I'm giving right now. Okay, in any case, this is the length of my vector, right? And so we said last time in the last lecture that you can write a vector as the product of its length and a unit vector. So actually, if we put the two bits of information we've gotten together, projection of u onto v can be written as the length, which is this guy right here, u dot v over length of v, and then times the unit vector v like that. All right. So that's it. That's our formula for the projection of u onto v. Okay. And again, it's nice and simple in that the dot product is easy to compute. The length of a vector is easy to compute, right? So the right-hand side of this expression is easy to compute. Okay. This expression is correct, but you actually see this expression in many different forms. Another way you might see it is like this, right? Where perhaps we just want to write it. It depends on what context you're working in, which expression is the one you want to use. But the second one is kind of nice in that everything to the left is just a number, and then everything to the right is just a vector. Okay. Another way we often write this, perhaps not as much in our class, but I can also write it like this. Right, same thing. I've just kind of moved things around a little bit. This is a nice way of writing it because in this expression, I have all my vectors here. The kind of v vectors are unit. All right, and this is actually a little bit kind of illuminating because it tells me that when I take u dot v, the length of v doesn't matter in this computation, right? Because when you look at this third expression, this guy's a unit. We've kind of reduced v to just a unit vector. We've reduced v to just a unit vector, right? So the length of v has been kind of erased from this expression if we actually just take this guy as a single entity and this guy as a single entity. Okay, so what that means is, in particular, when I calculate u dot v for these two vectors here, and then I take the same u and I dot it with, let's say, a vector in the same direction of v as v, but longer, so let's say maybe 3v, right? The projection here, projection of u onto v, is actually going to be equal to the projection of u onto 3v, right? Because ultimately, when you look at the formula, if you did this, if you calculated this guy, the 3's would cancel because you would have a 3v here, and then there would be a 3 down here. 3 here, 3 down here. Okay, so the length of the vector you're projecting onto completely disappears from the expression for the projection. Okay, and it makes sense because you're only caring about, you know, kind of how much of u is in this v direction. All right, so the length of u certainly does matter, right? If I change the length of u, the projection is definitely going to change, but not v. Okay, so that's our formula for the projection. Oh, by the way, I should definitely mention this. Projection of u onto v is definitely not the same as this. Oops. It's not the same concept as the projection of v onto u, right? Because one of them, v, u, this one on the left is a vector in this direction, okay? But the one on the right is a vector in the direction of u, right? So I'm projecting v down to here. So that's this guy right here. Okay, so projection of u onto v and projection of v onto u are typically going to be completely different. They're going to be vectors pointing in completely different directions. One in the same direction as v, the other in the same direction as u. Okay. All right, and again, I've drawn all these pictures with v and u, the angle between them being acute, but everything works exactly the same if they're obtuse. You just have to maybe, the projection would look something like this. I guess I should actually mention that. The projection would be that. Okay, that would be projection u onto v in this situation. So it actually points in the opposite direction of v, the direct opposite direction of v. But again, our formula takes that into account because our formula, in this formula, the u dot v, if u and v are in opposite directions, or if the angle between them is obtuse, then u dot v is going to be negative. And so what you end up with is this left-hand side is going to be negative, and then times a v. Okay, so you're going to get automatically that the projection is in the correct direction. All right. Let's see. Okay, so let's do an application. Let me do... Okay, yeah, let me do a kind of physics-y application first, and then we'll come back to another mathematical application. Okay, so the physics-y application is work. Let's say there's something lying on the ground right here, a box of something, And let's say I'm standing here. There's a rope attached to the box, and I'm pulling this rope. Okay, so I'm pulling the rope in this angled direction. And as I pull this rope, let's say I'm moving backwards. And of course, as we do this, the object is moving forwards. Okay, maybe a better way to say it, instead of pulling the rope, is I'm just holding the rope tight and I'm walking backwards. And of course, this object is going to move in the same direction as my motion. Okay, let me call the force of my pulling F, right? And again, it's a vector that's kind of tilted because, well, this object is on the ground and my arms are high up over the ground. Okay. The object is going to be moving, like I said, in this direction. And let's say it moves from here to here, right? Let me give this guy a name. Let me call it the vector D. Okay. So again, maybe the picture would be before is like this. Here's the object. After the object is here. Okay. All right. So it's kind of moved like that. And then I'm calling D, it starts here. I guess, sorry, they're not matching up that well. Maybe I make it kind of consistent like this. Right. Let's measure both of these from the tip, from the edge of the object. So where was my vector? Here to there. All right, so that's my D. Okay, so the question here is, well, okay, the issue here, the interesting thing here is, because I'm pulling this object kind of diagonally upwards, part of my effort is wasted, right? Because part of this vector F, I can break it down into a vector that's in the direction of the motion of my object and of a direction that's perpendicular to that. Okay, we're going to do that more precisely in the next mathematical example. But what we actually care about is this vector down here. The part of F that's actually kind of pulling our object from left to right. All right. The part of my force that's kind of pulling upwards is wasted. Okay. So that's is kind of fighting against gravity, right? But our object is not moving upwards. It's moving only to the right. Okay. So in terms of physics, when we talk about work, work done in this situation, only the part of the force that's in the direction of motion matters. Okay, and what is the part of force in the direction of motion? Well, let me draw the picture again. Here's the force, right? Here's my direction of motion. The part of the force in the direction of motion is exactly the projection of F onto D. Okay. All right, so let me actually calculate how much of the force that is being acted upon this object, how much of this force is actually kind of doing work towards moving it from the left to the right. Okay, so it's the projection of F onto D. So we just calculated that. That's going to be projection F onto D. And I'm just going to use the formula we just came up with, F dot D, right? Let me write this as, let me write it like this, length of D squared, and then times D. Okay. All right. Actually, let me actually write it like this. Sorry. Let me write it like this, so that this thing on the left is a unit vector. All right. So if we do this, then we can see that this quantity here is the length of the projection. And in terms of just a number, it measures how much of the force is doing something, right? Is working to move the object from the left to the right, right? So this guy here is the amount of force, amount of the force that actually matters in terms of moving the object from the left to the right. Okay. Now, perhaps in some previous class, maybe in high school or whatever, you probably talked about work as force over distance, right? So what you did maybe was you computed force pushing from a point or whatever from here to there, right? You've got your force. And what you did was if you calculated the force as a number, right, before you knew vectors, of course, right, you have F as a number, and then you have D as a distance. You multiply these two guys together, both as numbers, and you get your work. Okay, but now in this more advanced situation, what we have is this guy here is like the F down here. Okay, it's the number that represents how much of the actual force matters. And then, so let me write that here. So that would be like this F from whatever, from high school physics or something like that. And then if we multiply to D, right, that's going to be how far the object moved. What is that? That's the length of my vector D. Okay, so that's going to be length of the vector D like this. All right, so this is what you would have called in high school physics, the work, right? And notice one thing, these two D's cancel, and so it's actually equal to just F dot D. Okay, so even in this kind of complicated situation where a force is not necessarily pushing in the same direction, exactly in the same direction as the motion of the object, work has a very simple description, F dot D. Okay. And again, all of this makes sense because if your object is moving, slightly skewed from your force, then some of your force is not doing, the actual work in moving the object, right? So this part of the force actually, right there, is doing nothing with respect to the object being moved. Okay. By the way, why this part? Well, because this guy here plus that guy there, from the graphical definition of the vector of addition of vectors, this plus that is actually F. So we've broken down F into two pieces. The circled piece doesn't matter. This piece matters and is what comes into our, right there, in our work calculation. Okay. All right. Again, the example that I did, everything was nice and kind of simple in terms of acute angles and all that. But you can do the same kind of computations, forces like this, distances like that. Somehow the object is moving in the opposite direction. So you would be doing negative work, actually. So this angle is bigger than 90 degrees. And so F dot D is going to be negative. All right. Everything still works out. Okay. So you'll see maybe one or two, I think, homework problems, the online homework problems about calculating work. This is a kind of, again, a very simplistic situation, but in the near future, maybe in a few weeks, possibly even a little bit next week, we'll talk about work in a much more interesting and complex setting. So this is something we'll revisit quite a bit. Okay. Let's see. So something related to this, let's get back to just pure mathematics, is, I kind of alluded to it earlier. If we have two vectors like this, u and v, if v is a very important vector, it has some sort of importance associated to it, we often want to, talk about how much of u is in the same direction as v. And again, that's just a projection of u onto v. But also sometimes we care about this second vector that we just talked about, that's in this direction, right? And again, very importantly, this guy is a right angle. Okay, when we talk about the projection, the whole point of the projection is that this guy here is a right angle. Okay, or same as this angle right there. Okay, so oftentimes what we do is we want to break down u in terms of a piece that's in a direction of v, and then another piece, right? So u is equal to projection of u onto v. This guy is in the same direction as v, or opposite direction, right? When I say same direction, actually I mean literally the same direction or the opposite direction, okay? So this guy here is in the same direction. Perhaps I should say parallel, right? Parallel to v. We're not going to use that term too much, but I guess I'll try to stick with it for now. This guy here is parallel to v, and then plus something else, right? Again, we do this because perhaps we want to express things in terms of v. Now, the really nice thing here that's actually super important is that this thing right there, which is another vector, is actually, like I said, this dotted vector right there, right? Because again, this guy here plus this guy here gives me u in terms of just the geometric definition of vectors, okay? And what's important is that you'll see in terms of the picture, this vector here, that's this box, that I haven't even given it a name, is actually perpendicular to the projection, right? This is my projection vector over here. This is my box vector right there. They're perpendicular, okay? So these two guys are perpendicular. So not only does this projection allows me to write u as something in the same direction as v, but also plus something which is perpendicular to the first term, all right? You always, in math, we always like to break things down into, break a complicated thing down, for example, u, into a simpler piece, perhaps this projection, right? And I say it's simpler because it's it's expressed in terms of v, which, you know, has some meaning typically. And then plus something that's actually perpendicular to it. Vectors which are perpendicular interact very nicely. Well, in that their dot product is 0. So we very, very, very much like this kind of breakdown, right? To write u as something plus something else where the two things are perpendicular to each other, all right? One word you might hear in the future is orthogonal decomposition, okay? Now, the question is, what exactly is this box vector? Well, it's actually super simple. If this guy here, sorry, let me draw the picture again. It's getting a little messy up there. This is the projection of u onto v. This guy here is u. This is the vector that we're looking for. What is it? Well, projection of u onto v plus this mystery vector, right? Let me actually write this down. Projection of u onto v plus the mystery vector is equal to u, right? Well, what does that mean? That means this mystery vector is equal to u minus projection of u onto v. And that's it, right? It's actually kind of anticlimactic, but that's our mystery vector, okay? That goes right there. So now we're able to break down u into two simpler pieces, which those two pieces interact very, very nicely with each other. Okay, let me do a concrete example of this. So let's say u is equal to 1, 2, 4, and v is equal to 3 minus 1, 5. All right, so let's write u as the sum of two things, right? Where this guy is in the same direction as v, so parallel to v. And this guy is perpendicular to v, okay? Right, perpendicular to v, because again, here's our pictures. Here's a picture, that's my v, and you can see this guy here is perpendicular to v, all right? Okay, so parallel to v, perpendicular to v. Okay, so the first thing is just a projection, right? So the first guy here is just projection of u onto v, and all we have to do is just quote the formula, u dot v over length of v squared, right, times v. And I want to write it this way because cleverly, when I calculate the length of v squared, it's going to have a square, so I don't actually have to do a square root, all right? Because it's gonna be squared away anyway. So let me do the computation. U dot v is going to be 1 times 3, which is 3, plus 2 times minus 1, 2 times minus 1, which is minus 2, and then plus 4 times 5, which is 20. All right, so that's the u dot v on top. And then v squared, length of v squared is, again, remember that's, is, you can think of it as v dot v, or just, each individual term squared and then sum them up. So it's going to be 3 squared, which is 9, plus minus 1 squared, which is 1, plus 5 squared, which is 25. Okay, and then times v. Let me write it out. 3 minus 1, 5. Okay. So the projection is just going to be, let's see, 21 over 35. 3 minus 1, 5. And, oh, pretty nice. 3/5. 3 minus 1, 5. Okay. So that's how much of u lies in the same direction as v, or is parallel to v. Now, what's the other vector? The second vector, that's just going to be v minus this. So my second vector, I guess I've been calling it kind of mystery box. That's just v minus 3/5 of 3 minus 1, 5. Whatever that is, right? I kind of don't feel like computing this, but let's do it anyway. 3 minus 9/5, comma, minus 1 plus 3/5, comma, 5 minus 15/5, right? So that's going to be 6/5, comma, minus 2/5, comma, 2. All right, so ultimately we know that the vector, where's my u? 1, 2, 4. So ultimately our conclusion is that 1, 2, 4 is equal to 3/5 of 3, 1, 5, 3 minus 1, 5. Let me multiply the 3/5 in just to kind of make it so that it looks like just two vectors. Minus 3/5, 3, plus 6/5 minus 2/5, 2. Okay, where this guy here is parallel to v, and this guy here is perpendicular to v. Okay. All right. By the way, you can always check your answer. The dot product, because these two guys are supposed to be perpendicular, the dot product of these two individual terms should be 0, unless I've done an arithmetic mistake. Let me check it. So the dot product of these two is going to be 9 times 6, which is 54 over 25, minus, plus actually, 6 over 25, and then plus 6. Uh-oh, something terrible has happened. Because it's not 0. So I obviously made a mistake somewhere. Let me try to figure this out. Okay, I found the mistake. This is what happens when you try to be kind of too fast. This guy was wrong, right? It's supposed to be u minus the projection, u onto v, right? It's the leftover part of u. What's u? 1, 2, 4. So let me actually just write on top of it. 1, 2, 4. Let's see. 1 goes here, 2 goes here, 4 goes there. And 1 minus 9/5 is minus 4/5. How should I do this? You know what? I'm just going to erase all this stuff. I don't know why I didn't do this earlier. All right, erase the evidence of my mistakes. Okay, so This is just going to be, sorry about this, minus 4/5, comma 13/5, comma 4 minus 3, which is 1. Okay. And so ultimately we know that u, which was 1, 2, 4, should be equal to my projection, which was 9/5, comma minus 3/5. Sorry, that was a little messy. Minus 3/5, comma 3, and then plus minus 4/5, 13/5, comma 1. So that was my my perpendicular vector. And again, the importance is that this one here is parallel to v, right, using the notation from high school geometry perhaps, and this one here is perpendicular to v. Okay. All right. And you can you can check the dot product. Let's see if it's correct. This dot this is going to be 36 over 25 minus 13 times 3 is 39. So I get minus 36 over 25 minus 39 over 25 plus 3. Perfect. 39 plus 36 is 75, and so this is equal to 0. Okay. Let's see. So sorry about that little hiccup there. A couple more small things. So one thing you'll notice on the online homework is there's one problem where they ask you to calculate the projection of u onto v, kind of just like what we did just now. But they also ask for this guy here, SCAL u onto v. That's supposed to be scalar of u onto v, and that's actually just equal to the length of the projection. All right. This guy here is not standard notation, and in fact, usually there's no such notation for the length of the projection. So do the one homework problem that mentions this, and then forget that this notation exists completely. All right. So its only purpose is to do that for that one problem in the book. However, this projection notation is very standard, so you definitely want to get comfortable with it. All right, the last small thing is just a small mini note. Note that u plus v dot u plus v, like this. Right, this is perfectly legal because this left-hand side is a vector, right-hand side is a vector, and so you can dot two vectors together. This is equal to, so because of the properties of the dot product that we mentioned, they satisfy the distributive law and all that. This behaves very much like how multiplication of in algebra behaves, right? So you can write this as u dot u plus u dot v plus v dot u plus v dot v. Okay. Well, u dot v is the same as v dot u, right? We've talked about that. And u dot u is the length of u. V dot v is the length of v. So this is the length of u squared plus 2u dot v plus length of v squared. And again, this actually up here is the length of u plus v squared. Okay. So the one point here is that when you work with dot products, everything kind of feels very familiar, and it actually works out exactly like you would expect, right? If you had in algebra multiplied x plus 3 times x minus 5, same idea, right? X squared minus 5x, 3x, and then 15. So same thing here. Okay, so the formula looks almost exactly the same. However, the other thing I wanted to mention was if you do want to sit down and try to figure out where the formula u dot v equals length of u, length of v cos theta comes from. Like I said, it comes from the law of cosines, but one thing you might want to use is this expression here. Okay, because sorry, maybe not exactly this expression, but the one where this is a minus sign, where that's a minus sign. Okay, if we did do that, this would be a minus, 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 and that would be a minus. Okay, why would you care about that? Well, here's u, here's v, for example. What's I guess let me fix that one as well. Minus, right? What's u minus v? U minus v plus v is equal to u, right? So this guy here is u minus v. And so this creates for you a triangle. That angle here is theta, right? The length of this side down here is the length of u. The length of this side up here is the length of v. The length of this side here is the length of u minus v. And so using this expression that we just calculated, you can actually write that out. And then you can pop out the law of cosines in this way, or pop out the use of the law of cosines in this way. Okay, but do that only if you want to make yourself suffer a little bit. All right, so again, I recommend right now, or at least perhaps after doing the homework from 13.1 to 13.3, right? To do, actually, I do recommend right now to do the homework from 13.1 to 13.3. This is a summer class. It's twice as fast as a regular class. So if you kind of do what you normally do with a regular class, which I think most people do, is you just do the homework the day before the homework is due, you're going to be doing twice as much work as normal. And it's just very likely it's going to become really overwhelming. So I highly recommend perhaps doing kind of half the work, half the homework first, let's say by Wednesday night, and then doing the other half of the homework by the due date of Sunday night. So I highly recommend right now going to do the homework from 13.1 to 13.3. And if you do that, or you don't even have to have done that yet, but you can take a look at the add extra credit problem from paper homework, the one that you turn in through Canvas. All right, it's a fun little problem that gives you, again, like I said, a different perspective on perhaps on functions and perhaps also on vectors maybe, and gets you thinking about the nature of the dot product. And in the future, you'll definitely see that stuff again, particularly if you're going to be going into physics, mathematics, or engineering. Very useful stuff. Okay, so that'll be it for this lecture. I'm going to be doing 13.4 and 13.5, most likely as a single lecture, depending on how long 13.4 goes.